In the archives of Cold War planning, there is a recurring pattern that feels almost bureaucratic in its calmness. Columns of numbers, yield estimates, wind directions, casualty ranges written as intervals, not stories. The most unsettling feature of these documents is not the violence they describe, but how easily destruction becomes a matter of bookkeeping. Once force can be counted, it can be multiplied. Today, the world lives with the accumulated residue of that arithmetic. Thousands of nuclear weapons remain operational, most of them built during decades when strategic stability was defined by excess rather than restraint. Their individual designs vary, but their shared purpose is singular: to release energy faster than any natural process humans routinely encounter. The relevant question is not whether this power exists. It does. The harder question is what that power actually means in physical terms, beyond politics or fear. One way to understand scale is to step away from ideology and think spatially. The planet's population is not evenly spread. It concentrates into dense clusters of infrastructure, energy, food systems, and human bodies. Modern cities are not just collections of buildings, but tightly wound knots of dependency. Electricity grids, water treatment plants, hospitals, data centers, transportation corridors. Remove a few critical components, and the system fails even where walls remain standing. A single nuclear detonation over a major urban center does not simply destroy a city. It interrupts metabolism. Heat ignites fuel sources, pressure waves pulverize structures, radiation scrambles biology at the cellular level, and electromagnetic effects disable electronics that survive the initial shock. Multiply this process across thousands of locations, and the question shifts from destruction to redundancy. How many times over can the same systems be erased? From a purely numerical perspective, the answer is uncomfortable. The existing global nuclear stockpile contains enough explosive yield to erase the functional core of every large urban area on Earth and still leave weapons unused. This is not speculation or exaggeration. It follows directly from population distribution, blast physics, and known weapon yields. In engineering terms, it is not efficiency, but surplus, designed not for necessity, but for certainty. Yet raw totals conceal another truth. Energy does not behave politely when concentrated. Stack enough explosive force into one place, and it stops acting like a weapon and starts behaving like geology. The planet does not register intention. It responds only to energy transfer. Pressure becomes seismic. Heat becomes atmospheric chemistry. Solid ground behaves briefly like fluid. This distinction matters because it reveals the boundary between human-scale violence and planetary-scale processes. Most weapons are designed to interact with cities, not continents. But when yields accumulate, familiar categories fail. Fires merge into firestorms. Shock waves reinforce each other. Material once anchored to the surface is lofted into layers of air where weather, climate, and sunlight are regulated. At that point, destruction is no longer local. It becomes systemic. The unsettling implication is that humanity possesses not just the ability to end individual societies, but the capacity to interfere with Earth's long-established balances, temperature gradients, atmospheric circulation, biological recovery rates. The question is no longer how many people die in the first minutes. It is how the planet behaves in the years that follow. And that raises a deeper problem, one rarely addressed in strategic debates. What happens when human violence stops being a historical event and becomes a physical force, comparable to earthquakes or asteroid impacts? Imagine a remote stretch of land far from borders, shipping lanes, and cities. A place chosen precisely because it seems empty. No monuments, no skylines, no immediate political meaning. In strategic language, this would be called a neutral site. In physical reality, it is still a living surface layered with water, air, microbes, roots, and rock. The absence of people does not mean the absence of consequence. Now concentrate the world's nuclear arsenal into that single location. Not dispersed, not targeted, not optimized for efficiency, simply accumulated. The weapons themselves would occupy surprisingly little space. Modern warheads are compact, dense objects engineered for delivery rather than storage. The true mass lies not in their metal casings, but in the potential energy bound inside their cores. When such energy is released simultaneously, it does not resemble warfare as it is usually imagined. There is no sequence, no escalation. The physics are immediate. Within fractions of a second, matter at the center is driven to temperatures rivaling stellar interiors. Molecules do not burn, they dissociate. Solids do not melt, they transition into plasma. The concept of ground temporarily loses meaning. The initial fireball expands faster than sound, faster than any storm, consuming oxygen and radiating heat outward with brutal efficiency. Vegetation ignites not because flame reaches it, but because radiant energy overwhelms chemical bonds. Forests kilometers away enter combustion almost simultaneously, not as isolated fires, but as a single connected system. The atmosphere responds violently. Air compressed by the blast rebounds, forming shock fronts that flatten terrain in widening rings. These pressure waves do not stop when trees end. They propagate across continents, refracting through temperature layers, circling the globe multiple times. Instruments would record the event everywhere. Long after the light fades, the planet continues to ring. Above the surface, a towering column of debris ascends. Soil, ash, vaporized rock, and incinerated biomass are thrust upward into regions of the atmosphere that normally change only slowly. Here, gravity competes with turbulence. Some material returns quickly as scorching fallout. Other particles remain suspended, spreading laterally, dimming sunlight as they go. Radiation adds another layer of complexity. Short-lived isotopes deliver intense doses locally, rendering large areas immediately hostile to life. Longer-lived elements travel farther, diluted but persistent, integrating into rainfall, rivers, and food chains. The biological impact is uneven but global, less an apocalypse than a chronic injury inflicted everywhere at once. In the months that follow, secondary effects dominate. Firestorms inject soot into the upper atmosphere, altering how much solar energy reaches the surface. Temperatures drop modestly but perceptibly. Growing seasons shorten. Weather patterns shift. Ecosystems already under stress respond poorly to additional shocks. From orbit, the scar is visible but not dramatic. The planet is not shattered. Oceans do not boil. Earth continues to spin, indifferent to the cause of the disturbance. And yet something fundamental has changed. A human-made event has crossed into a category once reserved for volcanism or impacts from space. This is the unsettling lesson of scale. When enough energy is released at once, intent disappears from the equation. The explosion no longer represents policy or strategy. It becomes an experiment in planetary physics, one whose outcomes are governed by laws far older than civilization. And if this is the result of using what already exists, it invites an even darker speculation. What happens if the limits of material, not politics, define the upper boundary of destruction? To understand the outer edge of possibility, it helps to abandon realism for a moment, not in facts, but in restraint. Imagine a civilization that decides not merely to use its weapons, but to industrialize them without limit. Every accessible deposit of fissile material is mined. Every gram is refined. Every engineering shortcut is tolerated. The goal is no longer deterrence or defense. It is total yield. In Earth's crust, heavy elements are scattered thinly, but persistently. Uranium, in particular, exists in quantities sufficient to power reactors for millennia, or, under a different set of priorities, to manufacture an unthinkable number of nuclear devices. This is not conjecture. It follows from geological surveys and known extraction technologies. The bottleneck is not availability, but choice. Now compress the resulting arsenal into a single detonation. At this scale, Familiar comparisons fail. Individual explosions merge into one continuous release of energy. The fireball expands not just outward but upward, punching through atmospheric layers in seconds. The sky itself becomes part of the event. The surface beneath responds like a fluid struck by an immense force. Rock fractures faster than seismic waves can propagate. Entire sections of crust are lifted, accelerated, and in some cases vaporized. What remains collapses inward, forming a cavity tens of kilometers across. This is not a crater in the ordinary sense, but a temporary absence of structure, a region where solidity briefly ceased to exist. The atmosphere absorbs the next shock. Heat radiates outward with such intensity that distant air masses are driven to temperatures lethal to large organisms. Oxygen-rich regions ignite secondary combustion events far from the origin. Fire becomes global, not as a continuous flame, but as countless synchronized ignitions triggered by heat and falling debris. Seismic energy reverberates through the planet. Earthquakes ripple outward, interacting, reinforcing, and fracturing infrastructure on every continent. Coastal regions experience violent oscillations as ocean basins respond to displaced crust. Tsunamis are not singular waves, but chaotic sequences shaped by altered seafloors and collapsing margins. Above it all, debris escapes Earth's gravitational hold. A fraction of the planet's own substance is accelerated into orbit or beyond, forming transient rings of rock and ash. Some fragments rain back over weeks, delivering heat long after the initial explosion. Others remain aloft, silent witnesses circling a world that can no longer support complex life. The climatic aftermath is decisive. Sunlight is reduced to a dim, diffuse glow as aerosols and ash saturate the upper atmosphere. Surface temperatures plunge. Photosynthesis falters, then fails. Food webs collapse from the bottom up. Large animals disappear first, followed by smaller specialists. Even resilient species face starvation and poisoned environments. Radiation becomes almost incidental at this stage. It coats the planet, certainly, but the dominant killers are cold, darkness, and the breakdown of ecological continuity. Shelters, submarines, and bunkers delay the inevitable rather than prevent it. Survival becomes a matter of stored calories versus time, not protection versus blast. This is not a dramatic end marked by fire alone. It is a drawn-out erasure, unfolding over years as systems fail one by one. Civilization does not fall in a day. It starves, freezes, and fragments until there is no longer a collective entity to describe. At this extreme, humanity does not merely destroy itself. It interrupts a biological chapter that took hundreds of millions of years to write. And yet, even here, the planet itself remains, scarred, altered, but not broken, waiting, as it always has, for whatever comes next. Long after the last fire burns out and the final structures collapse, Earth enters a quieter phase. The violence that defined the end of the human era leaves unmistakable marks, but they are not eternal. Rain falls, winds move sediment, chemical reactions proceed without regard for memory. The planet resumes its slow, methodical habit of forgetting. In the centuries that follow, the surface remains hostile. Radiation levels decline unevenly as unstable isotopes decay into less energetic forms. Some regions recover faster than others. Life returns not as forests or animals, but as microbes, organisms that thrive in extremes and require little from their surroundings. They colonize cracks in rock, shallow waters, and the thin soils that begin to accumulate once temperatures stabilize. Geologically, the scars are obvious, but not dramatic. Large depressions fill with sediment. Melted rock cools into unfamiliar mineral structures. Layers of ash and debris settle into thin bands, pressed flat by time. From a distance, these strata resemble those left behind by ancient volcanism or asteroid impacts. Only their composition sets them apart. Embedded in this global layer is a peculiar signature. elevated concentrations of radioactive elements appear where they should not. Isotopes with no natural abundance linger as chemical ghosts. Alongside them are traces of materials that geology alone does not easily explain. Synthetic compounds, alloys, fragments of polymers that resist decay longer than the organisms that created them. Given enough time, millions of years, perhaps longer, complex life returns. Evolution resumes its slow experimentation, filling empty niches with forms shaped by new conditions. Intelligence, if it emerges again, does so without knowledge of what came before. Memory does not survive extinction. Only evidence does. At some distant point, a future species begins to investigate its world. It studies rock layers the way humans once did, reading history through pressure, composition, and anomaly. And eventually, it encounters the thin, strange horizon that encircles the planet, a boundary unlike any other in the record. This layer raises questions. Why does radiation spike so sharply and then decline? Why are heavy elements mixed in patterns inconsistent with natural processes? Why do residues of long-chain synthetic molecules appear alongside metals refined beyond geological necessity? The data resists simple explanation. Perhaps the researchers propose a massive volcanic episode, perhaps an impact, or perhaps something else entirely. A brief interval when a technologically capable species altered the planet faster than evolution could respond. A moment when intelligence acted not as a stabilizing force, but as an accelerant. From the planet's perspective, this interval is negligible, a blink in deep time. Earth has endured ice ages that lasted longer, impacts that delivered more kinetic energy, and mass extinctions driven by forces entirely indifferent to consciousness. Recovery, though slow, is not in doubt. What remains unsettling is not the planet's resilience, but the asymmetry between creation and destruction. It takes billions of years to produce a biosphere capable of reflection. It takes only decades to assemble the means to erase it. The ultimate lesson is not one of doom, but of scale. Humanity's greatest power was never the ability to destroy Earth. It was the ability to briefly rival natural forces and then vanish, leaving behind a geological question mark. In the end, the planet continues. The story simply changes authors.